I'd like to welcome you to this recording, the first on chapter 4 of Merriam and Craig, where we deal with, and let me just look at the title of the chapter in the book, Kinetics of Systems of Particles. This really means, since it's kinetics, and we've determined before that kinetics has everything to do with the application of Newton's second laws, this really means that we are going to study the application of Newton's second law to a system of particles. Now, why is this different, or in what way is this different from what we've done before? In the physics course, we have studied the application of Newton's second law essentially to a single particle, and that is also the way that Newton has initially stated his second law. But in this, we are now going to see how this can be generalized to a system of particles, and we really need this to be able to treat the dynamics not only of systems of particles but also of rigid bodies as a special case of a system of particles. Now, to address this, we need to start first of all by defining a system of notation, axis system, and so forth, and this is shown on this slide. So at this point, let me close off the video, and let's look at this system of particles, which is indicated by this funny shaped body that I've indicated on this slide. This, by the way, is also in the supplementary notes, and we are really going to treat the theory in terms of the supplementary notes. You should carefully take note of this, but you should also read the supplementary notes together with the handbook. So in the handbook, in the new in edition 7, it's on page 267. I'm not sure what the page number is in edition 6, but in any case, it's chapter 4 of both of these books. Now, this system of particles may be a rigid body, because a rigid body can also be considered as a system of particles, a body consisting of a very large number of particles. At this point, it's perhaps not too important to really consider what exactly is meant by a particle. Maybe it's one can think of it as the molecules, although I'm not claiming with this that we are going to study the dynamics of systems of particles on the molecular level. Or maybe you can just think of it as grains of metal, where each grain may consist of a number of molecules, or whatever. What the particle is in this context not too important, as long as we are happy to say that a rigid body may be considered as a collection or a set of a large number of particles. But this system of particles can also be a number of fluid particles, or it can be a number of particles of a gas. It can be a cloud. This can in fact be a cloud of gas particles that's floating in the air, or that's floating in outer space. So it can be a body of water that may be traveling through the air, like it can be a raindrop, or it can be, if I have a bucket full of water and I throw the water out of the bucket into the air, it can be that body of water that may be traveling through the air. So we are not limited to rigid bodies in chapter 4. So in that sense, chapter 4 is more general than chapter 5 and chapter 6 that follows, in that it looks at a system of particles in a much more general sense than just that of a rigid body. It includes, of course, rigid bodies, as I've said already. Also, we will be looking at this not only in planar motion. That's why we have a three-dimensional axis system, X, Y, and Z here. Of course, it's also a right-handed axis system. And we'll be looking at the motion of this, this set of particles in general in 3 dimensions, not only in planar motion. Now, let's consider a typical particle in this set of particles. I like to call this typical particle the generic particle, and it's indicated by this dot inside this body. And let's say that this generic particle has got a mass which is indicated by mi. The I is an index, so this it really means that my general or my generic particle is the ith particle in this whole set. And let's say I have got n particles in the set. That's quite often indicated by a small letter n. But this is the ith particle of this set. And this particle then has a position vector which would be the vector starting at the origin of my axis system and ending at the particle. And the position vector is indicated by the vector r. This is a r with a subscript I. The subscript I indicates the index I. Or in other words, it refers to the ith particle. And of course, since it's a position vector, it's indicated with a half arrow overhead as a vector. Now, if I think of this set of particles, of course I can calculate the center of mass of this whole system, and we'll be getting back to how this is calculated in a moment. But for now, let's just take it that we have a center of mass, and the location of the center of mass at this instant is this point here. Now, the center of mass may be inside the body. The center of mass, of course, may also be outside of the body. If I think of a donut, I'm sure all of you know how a donut looks like. But the center of the mass of the donut is actually not inside the donut, it's inside the hole in the donut. So it's possible that my center of mass may be inside the body, but it may also be located outside of the body, depending on the actual shape of the body. Now, the position of the center of mass, maybe I should first say the center of mass is indicated by the label G, capital G. And the position vector of the center of mass then, of course, is the vector starting at point O and ending at this position of the center of mass. And this is indicated by the symbol R with the subscript G, subscript capital G. And of course, it's also a vector, so we indicate that with a half arrow overhead. Now, once I've defined these 2 points, the generic particle position and the center of mass, of course I can then define the position vector of the generic particle relative to the center of mass. And that is given by this vector starting, of course, at the center of mass and ending at the position of the generic particle. And this is indicated by this symbol rho I. It has a subscript I because it's the relative position vector of the ith particle. And of course, it should be clear that I can define this position vector r sub I and rho sub I for all the particles in this system, and for each specific particle, the index in the subscript will simply change to indicate that specific particle. So I'll have a lot of these vectors r sub I. Well, of course, for each vector, the I will have a different value, the label of the different particles, and I'll have a large number, equal number of this rho sub I vectors. In fact, I will have as many rho sub I vectors and as many r sub I vectors as there are particles in my system. For each of those particles, I will be able to define its position vector r sub I and its position vector rho sub I relative to the center of mass. And of course, from this it's clear, and we'll use this later on, that the position vector of the particle r sub I, can be calculated as the vector sum of the position vector of the center of mass r sub G plus the position vector of I relative to G rho sub I. Now, we also define for later usage an arbitrary point capital P, which is this point here. Now this point can, it's really arbitrary, it can be anything. You'll later be in a position where you're going to choose the point P to be convenient for yourself for a certain application. So it's really an arbitrary point P, and the figure says that P may actually move. And of course then the position vector of this point P is indicated by this vector, the vector starting at O and ending at P, r sub P, and it's a vector, of course. And then after I've defined the arbitrary point P, I can say, well, that allows me to define the position vector of the center of mass of my system relative to the arbitrary point P as this vector starting at P, ending at G, indicated as r sub G slash P, indicating it's the position vector of G relative to P. And then the last vector on this slide that I haven't discussed yet is the position vector of the generic point relative to the arbitrary point. And that is indicated by a row with a prime. The prime distinguishes this vector from this vector, which is the position vector of the generic point relative to the center of mass. So to get back to P, the position vector of the generic point relative to the arbitrary point P is the vector rho I prime, and of course it's a vector because of that I have the half arrow overhead. And this vector starting at P and ending at the generic point. Okay, now since we've defined this sketch, and by the way, let me just interrupt myself, this is a very, very important sketch. So you must really study the sketch and make sure that you fully understand what this sketch means, what each vector in this sketch means. Okay, so if I then move on to the next slide, on this I'm stating that if I define the position vector of the center of mass as Rg, I can take its first time derivative. Nothing prevents me from doing that. And that, of course, I must then recognize as the velocity of the center of mass. If I take the time derivative of a position vector, I get a velocity vector. So the time derivative of the position vector of the center of mass is the velocity vector of the center of mass. Of course, it's a vector, therefore I indicate it as a vector. And nothing prevents me from taking the second time derivative of the position vector, which will then be the first time derivative of the velocity vector, which I have on the right-hand side. So Vg dot is Ag. So A sub G is the acceleration vector of the center of mass. And it's the first time derivative of the velocity vector. And of course, it's then the second time derivative of the position vector of the center of mass. Now, let's look at the definition of the center of mass position vector, this R sub G. We can say that R sub G is calculated as the fraction where the numerator is the sum of the masses of the individual particles, each multiplied by their own initial, by their own position vectors, and divided by, in the denominator, the sum of all the masses of the various particles. And why we define it like this, I'll get back to in a moment. It's just important at this point in time to realize that in general, the position vector is not a zero vector. Of course, it can be a zero vector if it just so happens that the center of mass of my system falls right on top of the origin of the axis system. Then my position vector of my center of mass will be a zero vector. But in general, that is not true. Okay, so let's look at how we derive, or how do we get at this definition of the center of mass position vector. This is really what this slide says. And to do that, let's go back to perhaps what you know, or what I hope that you may remember from defining the center of mass. I think in some other earlier course, perhaps in the physics course, you have defined the center, the position of the center of mass of a system of particles, and you probably use the symbol x bar, but in the context of this course, we will rather use x sub g. That is the position of the center of mass in the x direction, and perhaps you didn't work with bodies in 3 or even perhaps 2 dimensions, just thinking of this in a one-dimensional sense. The way that you've defined it before was to say, well, the position of the center of mass is simply the sum of the product of the masses of all the individual particles with their x coordinates. So it would be the sum of the products mi, xi, all of that divided by the sum of the masses of the individual particles. So this is a known definition of a center of mass position in the x direction that you've seen before. And perhaps you should also take note of the fact that in chapter 4 we're going to very often use summation notation like what I have here. And if you do not understand the summation notation, well, of course, it is important that you understand it. But if you cannot understand it, to help you to understand it, it's always convenient then, in order to aid the understanding, to write out the summation so that you can see what it means. So what does this summation in the numerator means? It simply means m1 times x1 plus m2 times x2 plus m3 times x3, etc., etc., until I've added to the numerator the product of the mass and the position of all the particles in my system. So this summation implies, it's not actually stated here in the notation, but it implies I'm summing over all the particles in my system, all n of them. So I could have also added the subscript I is equal to 1 and superscript n to indicate I'm summing over all the particles. But we think of this notation as that it goes without saying that when I write it like this, that I sum over all the particles in the system. So that's what the numerator means. What does the denominator mean? This simply means m1 plus m2 plus m3 plus etc. until I've summed over all the particles in the system. And of course, from this then it's clear that the denominator in this fraction is simply the total mass of the system. If I sum all the masses in the system, I'll get the total mass. So in the denominator here, or this sum mi, simply means the total mass of the system. Okay, so this is known, and let's then look at what I have next. It means that I can apply exactly the same rule in the y direction. I can say that the y coordinate of my center of mass is simply the summation of the products of the mi's with the yi's, the sum of the products of the masses of the individual particles with the y coordinates in the numerator and in the denominator once again, as before, the sum of the masses of all the particles. And in the same way, the z coordinate of my center of mass, if I now think of a body in not a body, let's call it a system of particles. It can be a fixed body, a rigid body, it can be a flexible body, it can be a body of gas particles or fluid particles. But the center of mass is in the numerator the sum of the products of the individual masses of the particles with their z coordinates, and in the denominator the sum of the masses of all the different particles. Of course, you should realize that if my body is not a rigid body, the body may deflect if it's a body of water or a cloud of gas particles, or even a flexible body of solid material, but it's flexible. Then it means that all these coordinates may change in time, and of course that means that my center of mass coordinate in the x and the y and in the z direction may change in time, just due to the deflection or the deformation of the body, but it may of course also change in time due to the possibility that the body may be moving through space. So x, g, y, g, and z, g may be functions of time due to either the deformation of the body or the motion of the body through space, or both. Okay, so once we've defined the x, y, and z coordinates of my center of mass, it allows me now to say that the position vector of the center of mass must simply be the x coordinate times the unit vector in the x direction plus the y coordinate times the unit vector in the y direction plus the z coordinate times the unit vector in the z direction. So I can define my position vector of my center of mass with this equation. And if I now substitute what I've just now derived above, I need to write it in this way. Of course, the three terms in this expression all has the same denominator, which is the total mass of the body. But I'll have the three vector components in the numerator, namely in the x direction the sum of mi(xi), in the y direction the sum of mi(yi), and in the z direction the sum of mi(zi). Now, of course, when I write these three summations, I can actually write this as a single summation, because I'm just adding all the terms in the three sums into a single summation. And if I do that, I can, if I look at the next slide, I can see that I can now, of course, if I write this as a single summation, all the terms in the x direction must be multiplied by the I vector. All the terms in the y summation must be multiplying with j, and all the terms in the z direction must be multiplying with k. But if I then write all these terms in a single summation, I see that a common factor in all the terms in the numerator is in fact the mass of the ith body. And if I then if I then realize this, I can group all the terms corresponding to a single body together, and to a single particle together, and then for that specific particle, in other words, for the generic particle, I can then factor out its mass from the three coordinates xi, yi, and zi. In other words, this is really just an application of the distributive law, but on the particle level. So in other words, to just put it in another way, once I write this as a single summation, I identify that I'll have for each particle three terms, one in the x direction, one in the y direction, and one in the z direction. And for each particle then, the three terms has the same mass, mi, and I can factor out the mi for those three terms. But note that I still have a summation over all the particles, so this is by no means claiming that all the particles have the same mass. A certain particle may have a certain mass, let's say the first particle will have a mass m1, and then I'll have a second term like this where I have m2 multiplying its coordinates, and I have a third, the mass m3 times multiplying its coordinates, all of that in a summation over all the particles. So just make sure that you understand that I can write this expression in this form. Now once I do this, I realize that what I have between brackets here is merely a description of the position vector of the ith particle. So I can write what I have between brackets simply as r sub I, the position vector of the ith particle. And with this then I've proven that my position vector of my center of mass, r sub g as a vector, is simply the fraction of which the denominator is the mass of the total system, and the numerator is the sum of the masses of the sum of the product of the individual masses with their individual position vectors. Now, what we've just now proven is repeated at the top left of this slide, and this allows me to then multiply this equation with the denominator on the right-hand side, which I recognize as just the total mass, and I indicate that with just the symbol m without any subscript. That's the mass of the whole system. So if I multiply this with the mass, I'll have on the left-hand side just m times rg as I have here. So it's the total mass of the system multiplied by its position vector. That must be then equal to the numerator on the right-hand side of the original equation over here, which is just the sum of the mi, ri vectors. And if I now, in this right-hand side, say, well, I know that the position vector of the generic point I can be written as this vector sum of the position vector of the center of mass and the position vector of the particle I relative to the center of mass, rho sub I. This allows me then to on the next slide, apply the distributive law to this expression, which says that this must be the same as the sum of mi times rg as a first sum, and then a second sum mi times rho I. Now, these two sums can be expressed as two summations, and the second one I'm not going to simplify now, but clearly here I have the second summation, the summation of mi with rho I. But the first, if I look at the first summation, the summation of mi times rg, I see that I've got n terms in that summation, where n is the number of particles in my system. But for each of those terms in the summation, I have rg as a common factor. The position vector of g is a common factor in all of the terms in the first summation. And because of that, I can take this r sub g out of the summation. In other words, I apply the distributive law and I factor out the r sub g outside of the summation. So I'm left here on the first sum, in the first summation in this, just with r sub g times the sum of mi. But the sum of mi is just the total mass of the system. So I can say that I've shown now that mg, that the mass of the system times the position of the center of mass is equal to the mass of the system times the position of the center of mass plus the sum of the masses of all the individual particles multiplied by their respective position vectors relative to the center of mass. The sum of mi rho I. Now, if I take this term to the left-hand side of the equation, it will cancel this term, and I then come to the conclusion, which is a very, very important point that I've proven here, which we're going to repeatedly use in this course. I've shown the identity that the sum of the products of the masses of the individual particles with their position vectors relative to the center of mass is equal to a zero vector. You can think of this equation as follows. If I start doing this summation, if I just look at the first particle, m1 rho 1, that will not be zero. If I now add to that m2 rho 2, I will still not have a zero vector. By the way, you should think of this as if I'm now like, let's say this is m1 rho 1, and then this is m2 rho 2, and let's say this is m3 rho 3, and then let's say that is m4 rho 4, and let's say that is m5 rho 5, and let's say that is m6 rho 6. I'll carry on like this, and I will never have a resultant. Now remember, the resultant vector is the vector starting at this point and ending at the tip of the last vector. If I carry on calculating this summation, I'll never have a zero vector until I add the contribution of the last vector, which will be, let's say, mn rho n, and if this system will allow me to draw an arrow like this, that will bring me back, and it's not showing it too nicely, but let me see if I can move it like this. Yeah. So the moment I add the contribution of the last mn rho n, the last particle to the summation on the left-hand side, I'll get back to the origin of my vector diagram, and the resultant will be zero. So if I add the product of the masses of all the particles with their position vector relative to the center of mass, I end up having a zero vector. Another way of thinking of the meaning of this is really to say, if I were to define a new axis system, a second axis system, and yeah, well, this axis system doesn't even need to be parallel to the original one. Let's say that's the x-axis of the new axis system. And let's say that is the y-axis of the new axis system. And let's say this is the z-axis of the new axis system. If I define a new axis system, but with its origin at G, and I calculate now, using this formula, but for the new axis system, the position of the center of mass of my system of particles in the new axis system. Of course, in that case, I'll, in this formula, not use Ri here, but I'll use rho I here. If I calculate this, I should get a zero vector because the origin of my new axis system is at G. But in the denominator in this equation, I'll have the sum of mi rho I. And the denominator, of course, will never be zero because that's the mass of the total system. But if I then calculate in this red axis system the position vector of my center of mass, the numerator better be zero because otherwise I'll have nonsense. And indeed, this theorem shows me that the numerator in this case will indeed be zero. But then I'll conclude just the slide by saying that this here is a very, very important relationship which we're going to use many times further on in chapter 4. Okay, let's just look at the notation and how this corresponds to the notation in the book. Of course, let's start at the right bottom. We've indicated that the position vector of the generic particle is just r sub I. In the book, it's indicated with the bold r sub I, but because the book generally uses bold symbols for vectors, but as we've said before, we cannot write a bold symbol with handwriting, so we'll indicate it as a normal symbol with the arrow overhead in handwriting. And so you need to always add the arrow overhead. If you just write r sub I, I'm going to mark it incorrectly. You're going to lose marks in the test and the exam. because I'm going off from the assumption that a person using normal handwriting cannot write a bold symbol. Now the position vector, let's go to the top left. The position vector of the center of mass is given by the R sub G. It's of course with a bold R with a bar overhead in the handbook. The position vector of the center of mass relative to the arbitrary point is given by R G/P in the supplementary notes. In the handbook they indicate this with a bold row with a bar overhead, as opposed to the position vector of the ith particle relative to the center of mass, which we indicate in the supplementary notes as a rho sub I vector. The handbook uses a bold rho sub I. And then for the position vector of the generic particle relative to the point P, where the supplementary notes use a rho sub I accent, the handbook uses a bold rho I accent. And then lastly, the position vector of the point P, the supplementary notes use R sub P, and the handbook uses a bold R sub P. But I'd like to stress that you need to, in your handwriting, always use the notation that we have in the supplementary notes that are indicated on the left of these 6 equations. Okay, so this brings us to Theorem 4.1. Now, the theorems are numbered according to the equations in the book. In other words, the Theorem 4.1 is a formal proof of equation 4.1 in the handbook. And let me just, to make sure, quickly check whether, yes, I've confirmed that indeed in the edition 7, the same equation 4.1 is the same as in the previous edition. So Theorem 4.1 proves equation 4.1 in the book. Now the background for this theorem is this question. We know that Newton's second law as postulated, we know Newton's second law as it is postulated for a particle. That is the way that Newton postulated it, namely that if I apply a force F to a particle of mass m, I can say that the vector F, the force vector, is equal to the mass of the particle times its acceleration vector. We know this. Now, the question is, can this law be generalized to apply to a system of particles? And I'm sure that you will respond to this positively. You'll probably say, well, yeah, we're doing this all the time. And that is okay, but, you know, is there any basis for doing this? In this case, our intuition will probably lead us to the right answer, and this theorem will perhaps show this. But you also should be careful, because we'll show later on in chapter 4 that our intuition can also lead us in the wrong direction. But so when we ask this question, we need to realize that if I have a system of particles, the particles exert forces on one another. We know that. We know that there are molecular forces between molecules. If I have a solid material, the grains, let's say I've got a metal bar, the metal grains in this bar exert forces on one another. And if I now apply Newton's second law to each and every particle in my system, I need to take into account these internal forces, we call it internal forces, the forces that the particles in the system exert on one another. We call them internal forces because they are actually forces internal to the system. But for each particle, it's a real enough force. It's a force acting on it caused by another particle. And if we have a system of 1,000 or 1,000,000 particles, do we need to really keep track of all these millions of forces which the particles exert on one another? That's the one question. Then the second question is, if we want to apply Newton's second law to a system of particles, what accelerations should we use? Now, if you think of this, many of you will probably say, well, we'll use the acceleration of the center of mass. And it turns out that that is the correct answer, but why? Why can't we just simply choose the acceleration of the center of mass? What makes the center of mass so special? Let's say we have a donut. The center of mass of the donut is not even part of the donut. Why is it so important? So we need to formally show that we are justified in using the center of mass acceleration when we apply Newton's second law to a system of particles. So that's what we try to do in Theorem 4.1. And our starting point then is to look at our system of particles once again, this funny shape, It's really the same drawing as we had before, just in a slightly more simpler form, since we don't have the arbitrary point P in here. The other vectors have the same meaning. And if we now look at a typical particle, at the generic particle of mass Mi, I can see that there will be, in general, a number of forces acting on this particle, and this is what is indicated by this figure. So I'll have, let's say, capital Fi1, where the I, the subscript I, indicates it's a force acting on the ith particle, and the 1 indicates it's the first force. Now, we use the notation with a capital F to indicate it's an external force. All the external forces are indicated with a capital F. So in general, I can, let's say, have a certain number of external forces acting in different directions on the ith particle. So in this example, just 3 are indicated: Fi1, Fi2, and Fi3. But it can be more than 3. But these are all the external forces acting on the ith particle. But then we also know that on the ith particle there are also a number of internal forces. In general, all the particles in the system exert forces on the other particles in the system. So I'm using the small f to indicate the internal forces, internal to the system, the forces that the particles exert on one another. And here the notation means small f sub I means it's a force, once again, a force exerted on the ith particle, but the second subscript 1 indicates it's the origin of that force. In other words, this is the force exerted on particle I by particle 1. And this is the force exerted on particle I by particle 2. And this is the force exerted on particle I by particle 3. And of course, in general, if I've got n particles, I will have n minus 1 forces like these, since, of course, the particle I doesn't exert a force on himself. So if I've got n particles, I'll have, in general, n minus 1 of these internal forces. Okay, so having said that, I can now state Newton's second law for this particle only, just for this particle. So on the right-hand side, I should have its mass times its acceleration, which I have. There's the mass of the ith particle, and I've got Ri, the position vector of I, with 2 dots overhead, which means it's a second time derivative of its position vector, which is its acceleration vector. So on the right-hand side, I've got the typical Newton's second law, mass times acceleration for the ith particle. On the left-hand side, I better now have the sum of all forces acting on the particle. So let's say I've got K forces, K external forces acting on particle I. So this first term on the left-hand side is the sum, the vector sum of all the external forces acting on the ith particle. And then the second summation on the left-hand side is the summation of all the internal forces acting on the particle I. So this is a summation of f sub I, j, for j from 1 to n, except for the case where j is equal to I, because when j is equal to I, there isn't a term like that, because of the fact that the particle I does not exert a force on himself. So this equation, you should be happy, you should be clear in your mind, is a statement of Newton's second law for the ith particle in our system. Now, if we can write this for the ith particle, we can also write it for any other particle in the system. In fact, we can write this equation for all the particles in the system. In other words, for I, remember I here indicates the ith particle, but this equation can be written for I equal to 1, 2, 3, etc., up to the nth particle, where we have n particles in our system. Now, so this really means that we've got n of these equations. And what we can now do is we can add all of these equations together. So if we sum over all these particles, by the way, the top equation on this slide is simply the bottom equation from the previous slide. If I now sum over all the particles in the system, of course I have a double summation on the first summation, because this is just the summation of the external forces in the ith particle, but this is then a summation over all particles. And likewise for the second term, this in between the brackets is really that term. It's the summation of all the internal forces working in the ith particle, but then I sum over all the particles. And on the right-hand side, the same way, I'm summing the masses times acceleration vectors of all the individual particles from the first one to the nth one. Now if we just look at the internal forces carefully, realizing that if the ith particle, or let's say if the jth particle, exert the force on the ith particle, which is indicated by this part of this little sketch. This is the ith particle, and F sub ij is the force acting on particle I caused by particle j. If I have this force, of course I must have an equal but opposite direction force on particle j caused by particle I. So this is the force acting on particle j caused by particle I. And by Newton's third law, these two forces must have the same magnitude but have the opposite direction. So as vectors I can write this expression, that F sub ij is equal to minus F sub ji. Of course, where both these F's are vectors, force vectors. If I realize that, and I consider once again this summation, I realize that this summation is simply a summation over all the internal forces in the system, but all the internal forces appear in pairs of equal magnitude and opposite direction. So the moment that I sum over all the internal forces in the system, I have a zero vector. So I come to the conclusion that this whole summation is just a zero vector. All the internal forces summed together gives me a zero vector, and I can therefore ignore the internal forces. That is really the conclusion that we come from this. So this means that our summation over all the particles simplifies to this equation, which really says on the left-hand side, the summation over all external forces on the system must be the same as the summation of the products of all the mass particles with their respective acceleration vectors. So this is still not a very convenient equation. On the left-hand side, it's okay. We just have the summation of all external forces over the system. We can probably not simplify this too much, but it's not too difficult to figure this, because quite often you don't have a very large number of external forces acting on the system. It may be 2 or 3, or may even be a single external force. The external forces are limited, so normally the left-hand side is not difficult to calculate. The problem, however, sits on the right-hand side, because if I have got a system with 1,000,000 particles, I need to calculate the 1,000,000 accelerations and multiply them with 1,000,000 masses, and then add all of them together. So the right-hand side is not too convenient to work with, although I must also stress at this point, sometimes we will actually use this form of the right-hand side. Sometimes, if the number of particles in the system is limited, it's actually quite meaningful to use the right-hand side in this form. But for general use, we're going to simplify the right-hand side further, at least we're going to try to simplify that further. And so to do that, let's look at the definition of the position vector of the center of mass, as we've done it earlier in this recording. If we take the second time derivative of this equation, of course I've multiplied this with a mass in the denominator to get the equation on the right-hand side. But this really is just after multiplying this whole equation by the mass, and then taking the first and then taking the second derivative, I see that the summation of the product of the masses of the individual particles with their respective acceleration vectors is really the same as the total mass of the system multiplied with the acceleration vector of the center of mass. And so since we have this this summation on the right-hand side of our equation on the previous slide, let me just go back. You see there we have this. We've now expressed that as the total mass times the acceleration of the center of mass. We can substitute this back into the equation, which means that this form can now be expressed as this equation, which really says that on the left-hand side we've got the sum of all external forces, or the resultant of the external forces acting on the system, is equal to the total mass of the system multiplied by the acceleration of the center of mass. And this is then really what is given in equation 4.1. So this is then Theorem 4.1, stating in a more simpler form the resultant force of all external forces acting on our system of particles is equal to the total mass of the system multiplied by its acceleration vector. And this is the end of this set of slides, but it's not the end of the recording. So let me try to get back to this. I need to now get a different set of slides to application sharing. I must stop application sharing, and I must just select a different set of slides quickly. And let me now start sharing again and select this. Let's hope this works. Yes, okay, so there I have my first sample problem. Now let's look at this. In the new book, in edition 7, a new sample problem has been inserted as sample problem 4.1, and it's a very nice example. I'd like you to, on your own, for self-study, work through just the first part of this, the first 3 lines of the solution of sample problem 4.1. We will make a copy of this and put it on the web for the students using the 6th edition. But it's a very nice problem, and it first calculates the position vector, then the velocity vector, and then the acceleration vector of a system of 4 particles. And I'd like you to work through this on your own, only up to the point where you calculate the acceleration vector of this system of particles. Make sure that you understand it's done fully in vectors in 3 dimensions. It's a very nice example. Please work through this up to the point for now, up to the point where the acceleration vector is calculated. I'd like to now discuss sample problem 4.2 in edition 7, which is the same as sample problem 4.1 in edition 6. And what we have here is a system consisting of 3 particles. Each of them has a mass of m. The mass of the 3 particles are the same, it's the mass m, and they are fixed to rigid bars of length r, three rigid bars that are welded together at a certain point in such a way that the angle between, maybe I should also say it's welded in such a way that the bars and the 3 masses all lie in a single plane, and so that the angle between the bars are 120 degrees. And they show in this drawing these bars with an axis system, a y and x axis system, with the origin of the axis system O at the point where the 3 bars are welded together. Now the length of the bars, I'm not sure whether I've mentioned that, is the same for each of the bars. It's a distance r. And then they tell us that at a certain point in time, a force F is exerted on the bar of one of the balls, or one of the masses, the one that's aligned with the y-axis, and this force is applied at a distance b from the origin, or the b from the point where the bars are welded together. And we are for now only going to answer the first part, the part A of this sample problem. We will be getting back to the part B a little bit later. But part A tells us for this situation of applying the force F at this point B, we need to calculate the acceleration of the center of mass of the system. Now, if we calculate the position of the center of mass of the system, and we don't even need to calculate that, we can say from inspection that the center of mass of this system lies at the origin of this axis system, lies at point O, at this point where the bars are welded together. So they want us to calculate the acceleration of this center of mass when a force F is applied at this point, a distance b above the center of mass. And we should now think of this in a gravitational-less field. There are no gravitation forces, so it's as if these 3 balls are in outer space. That's one way of looking at it. Or alternatively, you can think of this as that, yes, there is gravitation, but these 4 balls lie in a horizontal plane on top of a table. So in that case, gravitation will be working. The view that we will have here will then be looking down on the table, and the gravitation force on the 4 balls will be into the table or into the plane of the screen or the plane of the paper. But of course that will be reacted by the reaction force of the table on the balls coming out of the plane of the paper or out of the plane of the ball, plane of the screen, so that the weight and the reaction force of the table are in equilibrium, and they then do not contribute to the resultant force. So the resultant force on this whole system is just this single force F. So the equation that we're going to use is simply equation 4.1, which we've proven in Theorem 4.1, which says that the resultant force on the system of the particles must be the mass of the system times the acceleration of its center of mass. And so in this case, the applied force is the scalar F, the magnitude of the force, in the I direction. So that must be the same as 3 times m times the acceleration of the center of mass. Note that there's some ambiguity here with respect to the symbol m. You should understand that in the statement of the equation, this m indicates the total mass, whereas in this equation, this m indicates the mass of the individual balls, and therefore the total mass is actually 3m. As long as you are aware of this ambiguity, you should be fine. Now, in this equation, we can then isolate the acceleration on the left-hand side, the acceleration of the center of mass, which is also the acceleration of point O, and that will then simply be F, the scalar F divided by the scalar 3m in the I direction. So this is the answer to the question. Note that the notation of O is also ambiguous here because of the fact that we've reserved O for the origin of a fixed axis system, and in this case the axis system is not fixed. The axis system is really connected to the system of particles, and it's accelerating with the system of particles. So that's why we can talk of the acceleration of O in the more general sense, in the way that we've defined our axis system in the beginning of the supplementary notes of chapter 4. The center of or the origin of the axis system cannot have an acceleration. It's a fixed axis system, so the acceleration of the axis system origin is 0. That is not what is meant with this A sub O. In this case, it's an axis system that's accelerating with a body. It's not the fixed axis system that we were talking about earlier. Okay, so let's now look at another example, and this is in the example set after this section in the book, specifically it's sample problem, sorry, not sample problem, class example 4.6 or problem 4.6 in edition 7, which is problem 4.4 in edition 6. And what we have here is given by this diagram. It's a set of, or it's a number of 3 monkeys, which are, the 3 monkeys are labeled A, B, and C, that are climbing up or down on a rope that is suspended from the ceiling at point D. Now it's given to us that the monkey A has got a mass of 10 kilograms, the monkey B has got a mass of 15 kilograms, and monkey C has got a mass of 8 kilograms. Furthermore, we are told that monkey A is, as it's climbing down the rope, is accelerating downwards with an acceleration of 2 meters per second. Now you see that there's an eye here. I've redrawn the sketch on the left here, and I've selected to use an x-axis pointing downwards. Note, this is perhaps not the way that you normally draw axis systems, but now remember that you are free to, and I'm free to, select an axis system just the way we like, as long as it's a right-handed axis system. Now this problem is really a one-dimensional problem, so we're not even going to work with the y or with the z-axis, but there's nothing that prevents me from selecting my x-axis downwards. And because of that, I can say that since the monkey A is accelerating downwards, its acceleration vector, A sub A is 2I meters per second squared. The monkey B is given that it's climbing upwards with a speed that is known. It's given in the problem statement. I'm not even sure what the speed is, but it's given in the problem statement. The point is the speed of this monkey is actually irrelevant, but it stated that this monkey is climbing at a constant speed, which means that its acceleration vector is 0. So therefore I can write that AB is a 0 vector. And then lastly, the monkey C is also climbing upwards, but he's climbing up, he's accelerating upwards with an acceleration of 1.5 meters per second, which means that his acceleration in the x-axis system I've chosen is minus 1.5 I meters per second squared. And they now ask us to calculate the force in the rope where the rope is attached to the ceiling. That is the problem statement. Now to answer this, I'm going to draw a free body diagram. You've learned about free body diagrams in mechanics. We certainly didn't use free body diagrams in chapter 5 because we were not solving for any forces. We were not, in chapter 5 we were treating kinematics, and kinematics has got nothing to do with the forces causing the motion or resulting of the motion, and because of that the free body diagram was never used. In chapter 4, however, and also in chapter 6, when we deal with the kinetics, when we deal with Newton's second law, we need to deal with the forces on the system, and for that we will usually use a free body diagram. So if I draw a free body diagram, it means that I cut the rope just below point D, and at the cut I then need to insert both on the ceiling side and on the free end of the rope where I've cut it, I need to insert the internal forces in the rope, which is the force T, and which is really the unknown that we'd like to calculate. So we are now going to just use this part of this. Maybe I should draw a rectangle around it. When I say that I talk of a free body diagram, I really just talk of this part here, the part below the cut, and at the cut I've got the upwards force T, which is the unknown that I'd like to calculate. And then on my free body diagram, I also of course need to indicate the weights of the three monkeys. So for the first monkey A, its weight is M sub A times G. At monkey B, I've got a weight force M sub B times G, and at monkey C, M sub C times G. So these are the forces of the weight and then the force in the rope. And these are the only forces acting on this whole system. All the forces acting on the system are these four forces. And now I'm going to apply Theorem 4.1 in order to calculate the unknown force T, because the weights of course are really known. I can easily calculate the weights. Now I know that on the right hand side of equation 4.1 I have the mass of the total mass of the system times the acceleration of the center of mass, not what I've written here, but the total mass times the acceleration, which is really what I've written here. So this is on the right hand side of equation 4.1. In this case, it's inconvenient for us to use the acceleration of the center of mass because we do not know what the center of mass acceleration is. So it's convenient for us to rather use, in this case, the summation of the since we just have three particles, the summation over the three particles of their respective masses multiplied by their respective accelerations, because we do know the accelerations of the three particles in our system. In this case, our system have the three particles are really just the masses of the three monkeys. We really ignore the mass of the rope. We argue that the mass of the rope is negligible compared to the mass of the monkeys. So we consider our system as consisting just of the three monkeys. And so we can say then that the sum of the product of the individual masses with their accelerations must be the first monkey mass 10 times acceleration 2, plus the second monkey mass 15 times acceleration 0, plus the third monkey mass 8 times acceleration minus 1.5. All of this times I, because these vectors are all in the I direction, and the units of this then of course is kilograms times meters per second squared. And if I then, on the right hand side here, I have something that I can calculate. If I do that, I find a value of 8I Newton. And I write Newton here simply because kilogram times meter per second squared is Newton, but you should really not think of this as a force. This 8I is actually not a force. It's really a summed mass times acceleration. Its units turns out to be a force, but it's not a force. And we shouldn't think of it as a force, because the moment you start thinking of this right-hand side of equation 4.1 as a force, you run into trouble, because the forces all needs to be added up on the left-hand side of the equation. So don't do that. Don't think of that as a force. Keep it on the right-hand side. It's the masses times accelerations. And this, of course, we can then say is the same through this equation as the total mass of the system times the acceleration of the center of mass. Okay, so if we now look at the left-hand side of the equation, left-hand side of the equation says that the resultant force must be equal to the mass times the acceleration. So for the left-hand side, here's the equation 4.1. We need to calculate the resultant force on the left-hand side of the equation. Now, we only have the four forces. The first one is the mass of monkey A times G, plus the mass of monkey B times G, plus the mass of monkey C times G, all of them in the positive I direction, minus T in the negative I direction. So if I calculate this, I get a value of 323.73 minus Ti Newton. And now I can equate the force, the resultant force on the left-hand side, to the mass times acceleration of the center of mass on the right-hand side, which we've calculated as 8I. Let me go back. My link didn't work. On the previous slide, we calculated as 8I Newton. And if I then substitute on the right-hand side what we've calculated, we see that we can now calculate the dot product of this equation with I. And from that we can then solve for the unknown T as 315.73 newtons. And with this we have solved the problem. And with this I also conclude this lecture and this recording.